Hi there. Let's talk about Titanic Computers. I'm Eric Steinhardt, and you can learn more about me at my website, www.ericsteinhardt.com. We're going to talk about Emil Post. And Post was a Polish-American mathematician, lived from 1897, tragically died young in 1954. He discovered a theory of universal computation independent of Alan Turing or Alonzo Church. And there's a picture of Post right there on the left. So for Post, what is computation? Well, computation is string rewriting. Here's what I mean by string rewriting. String rewriting uses what are called production rules, and a production transforms a string into a string. Here a string is a sequence of symbols, a sequence of zeros and ones, a sequence of letters from the English alphabet, or just some other sequence of glyphs or individual symbols taken from an alphabet. Here are some examples of production rules. We have A followed by another A. Now the plus sign means that these are two distinct strings. Right? It's not analogous to arithmetical addition, but it means that we have two distinct strings there, two A's. We could use a comma instead of a plus. So A plus an A, they come together and they're transformed into one string, AA. Two strings become one string. Here's the string AA, which gets transformed into ABA. And that would mean that wherever you find an instance of AA, you transform it into ABA. Here's the string AB that gets transformed into two distinct strings, AA and BA. Those are just some relatively trivial examples of string rewriting rules. So where are we going to find post computers in the universe? Where are we going to look to find them? Well, let's start with our solar system, solar computers. How would there be computers in the solar system? Well, look at the sun. Look at the core of the sun. What does the core of the sun do? It fuses hydrogen. It takes a hydrogen 1, right? That little superscript 1 before the hydrogen 1, meaning it has one particle in it, one proton. Takes two hydrogen 1s, fuses them together, and gets a hydrogen 2, a deuterium atom, right, with a proton in red and a neutron in gray. Now that collision, that fusion reaction also puts out a positron, the little white dude there, and a little bit of radiation signified by the Greek letter, the little V-looking letter up above. But basically we have two hydrogen 1s collide and fuse into one hydrogen 2. Now we can write it like that. We can write it as a string rewriting rule, right? In fact, we could just drop the 1 in front of the H or the 2 in front of the H. It looks also like an addition rule. 1 plus 1 gets transformed into 2. Fusion to helium-3, a deuterium atom and a regular hydrogen atom. They come together to make helium-3, which has two protons and one neutron. There are the reactions, the atomic reactions. H plus H leads to an He, and here we're actually thinking of the atoms themselves, the nuclei themselves, as the strings, right? The string is actually the little red and gray balls. But again, this is arithmetical. 1 plus 1 gets 1 plus 2 gets transformed into 3. Fusion to helium-4, we've got helium plus helium gives us helium-4 plus a hydrogen and a hydrogen. 3 plus 3 gets transformed into 4 plus 1 plus 1. So this is not quite the same as addition, right? This is like moving things around on an abacus where the the symbols in the alphabet are like little pebbles on an abacus, and you take two groups of 3, put them together, divide them up into one group of 4 and two 1s. Okay, a little more complex, helium into beryllium. We've got the two helium atoms coming together and fusing into beryllium. That's 4 plus 4 getting transformed into 8. You can go all the way up, of course, to uranium, plutonium, and so forth with these kinds of nuclear fusion reactions. And the fusion reactions, very interestingly, right, those reaction arrows show that the stellar computations, right, the computing going on in the cores of stars, not just our sun, of course, but the computations going on in the cores of stars are algorithmic, and they are generating an algorithmic output. They are generating an output that looks very much like that line of black stair steps, right, between the blue and the orangish brown, right? That's the line of beta stability. That's the line of stable atomic nuclei. And it's very interesting that you should see a line like that. That's a very non-random structure. This computation is not random. It's not atoms randomly moving in the void. This is atoms coming together through reactions that are computing an algorithm that produces a highly non-random structure. Let's go now to planets, right? Solar systems often have planets in them. Then what are planetary computers like? Where would we find, what kinds of computations go on planets? What kinds of post-rewriting rules are on planets? Well, planets do chemistry. These are obviously some simplified chemical reactions. We have water splitting into hydrogen and oxygen. We have two water molecules, that's the HOH and the HOH. They get transformed by the chemical reaction, splitting water into HH and HH and OO, all right? So that's a string rewriting rule. Chemical reaction, this is the burning of methane, right? The methane is CH4, which is just HHCHH, that's a string, plus two O2 molecules, which is just the OO and the OO, and that gets transformed into OCO plus HOH plus HOH. In other words, into one carbon dioxide, CO2, and two water molecules, two H2Os. Again, that's a string rewriting operation. Here's one that's a little more complex. This is what happens when you pour vinegar onto baking soda and you get sodium acetate water and that good fizzy carbon dioxide. So that's a more complex kind of chemical reaction, but still we could spell it all out. It's still a post-style string rewriting rule. It's still a production rule. What about the Earth? Let's go to the Earth. That's a planet, digital Earth. What are we talking about? Digital Earth is a kind of post-computer, right? A post-rewriting system. How's that work? Earth has DNA, right? From atoms to DNA. Look, there it is. There's a bit of a strand of DNA spelled out at the atomic level, all those little dots being atoms, and you can see it broken out as the, A, T, and C, and G, right? The different the different base pairs in the DNA, all those little atoms and how they're bonded together. So that's complicated. Let's simplify it. And there's some DNA. You see A pairs with T, right? The green pairs with the purple, and C pairs with G, right? The pink pairs with the blue. And there's the backbone of the DNA, the double helix, right? How it wraps around itself twice like that. DNA is digital. It has 4 letters, A, C, G, and T, and each letter can be coded as 2 bits, 00 for A, 01 for C, 10 for G, and T is 11. So we can spell out a string of DNA base pairs as bits. So we just translate it, right? If we have ATT, that becomes 001111. And CGC becomes 011001. DNA, of course, replicates by dividing its 2 strands and generating, right, a couple of offspring strands. This is very complicated, right? It's a complicated process involving lots of proteins and lots of structures. It's really proceeding from the right to left there. The original parent strand on the right is getting divided by that helicase triangle, right? And then each of the offspring strands pairs with its complement to make 2 new offspring strands. We can simplify this, right? Going now left to right, we have the parent strand unraveling, and now the 2 offspring or daughter strands are forming on the right, right? So DNA is just dividing, it's just splitting. This is asexual reproduction, and of course it happens like this. We have 2 strands bound together, right, by complementarity. They split into the single strands, which then recombine, thus reproducing the original. And that's basically a post-rewriting rule. The parent double strand becomes 2 offspring double strands, right, 2 copies. Right, so the parent goes to an offspring plus offspring. With sexual reproduction, of course, you have the male and the female. They come together and form a single offspring, right? You take part of the male DNA and part of the female DNA, mix them together, that good sexual mixing. And we have, for instance, up the top, that's the male, we're going to take the ATT from the male, and then down at the bottom we'll take the CGG, right, and we'll get a new strand, ATT-CGG, with its complement over on the right. So that's male plus female strings leads to a single offspring string. And that gives us the whole tree of life. There's an early version of it with plants and protozoa and animals from Ernest Haeckel. That's a little obsolete, of course, and it's quite old. But here's, it's spelled out. You see these kinds of phylogenetic trees. This is just for some mammals. It's obviously very highly simplified, but you see platypuses. Who doesn't love platypuses? Elephants, right? Primates, where we come off that little primate branch. There's rats and there's zebras and, cats and felines, canines, and seals. Wow. And so a bunch of mammals there, even whales there. All right. And so a full, more spelled out tree of life, of course, would be enormous, right? There it is in the classical circular diagram. And there might be on other planets, no reason to think Earth is the only planet where there is life. So if computations are running like this everywhere, why not on other planets with their own strange biological computations, their own alien forms of life? So I'm Eric Steinhardt. We talked a little bit about post-computation and how there can be Titanic computers in our universe. Thank you very much.